This is the video demonstration for the component proof of concept B1 of Hexa-X-II. This video demonstration focuses on orchestration mechanisms of an open-source, distributed, latency-sensitive application. Its operation will be presented along with its two associated workflows, an object detection workflow and a video streaming one. The first is orchestrated using a set of autoscaling and computation offloading mechanisms over interconnected multi-cluster setups, including a scenario with infrastructures from different providers requiring service federation. The second will be used to demonstrate a high availability scenario on top of an emulated extreme edge infrastructure. The aforementioned scenarios are executed on a 3-cluster testbed located in the ICCS laboratory. The virtual setup includes one Kubernetes cluster with sufficient resources and one K3s cluster with lower resources. The two clusters are coordinated by the Karmata Multi-Cluster Manager for enabling multi-cluster deployments. An observability server has been deployed to provide real-time access to the collected metrics for the intelligence components that utilize it for their operation. The third cluster is implemented by the ILE. The ILE is a software component to emulate the features of future 6G networks, allowing to deploy high number of nodes of different types, with clearly separated stakeholders and network domains. It emulates the extreme edge node's volatility and allows to deploy realistic network services. It is structured with the back-end and front-end, and each of them can run on different premises. The containers in the back-end generate information that is consumed by the front-end and represented through an interface. This is how the graphical user interface looks like, with separated stakeholders, network domains, and services. For demonstrating the different mechanisms developed in Hexa-X-II, a smart manufacturing application for managing the operation of a static robotic arm was developed. It is composed of two main workflows, one regarding teleoperation of a robotic vehicle surveilling the workspace of the arm and a second regarding the generation of alerts to safely pause and start the operation based on animal-based object detection component analyzing the video stream of the vehicle. The object detection workflow is composed of two main components: the frame sampler, which samples the frames from the stream with a configurable sampling rate, and the object detector, which analyzes the frames and generates alerts in case of an emergency. During normal operation, the robotic arm performs a given task in a loop. At the same time, the vehicle is remotely controlled to monitor the space around the arm. In case a person enters the area and is detected by the object detection component, the rate of the analyzed frames is increased and consequently the end-to-end application latency increases. Then, the reinforcement learning-based auto-scaling mechanism is triggered to efficiently scale up the object detector to accommodate the increased demand. For cases where the resources of the edge cluster are not sufficient, the mechanism is trained to also identify the optimal cluster to place the replicas, in this case the cloud cluster. The migration of the service between the two clusters is realized using the Karmata management tool. When the person comes out of the frame, the arm resumes its operation. The autoscaler is then triggered by the workload decrease to scale down and place the object detector back to the edge cluster. In the previously demonstrated scenario, when the auto-scaling mechanism is triggered to efficiently scale up the object detector and place it to a different cluster, inter-cluster connectivity was established and maintained using the Karmata multi-cluster management tool. For demonstrating additional inter-cluster communication scenarios, the following technologies are also explored. First is the network service mesh, serving as an IP service mesh enabling the interconnection of workloads running in multiple clusters. It achieves this by working in parallel with the existing CNIs and by requiring no changes to the existing workloads. If one cluster has limited resources, an AI algorithm could choose to deploy a workload in another cluster. For example, the frame sampler runs in cluster 1, and the object detector is placed in cluster 2. In this case, an SM can be used to automatically facilitate network connections across clusters. To do so, it needs to add simple annotations to the pods. If a pod with an annotation is deployed, the tool will automatically inject an SM clients into it. These clients allow the workloads to request access to the network services, even when placed in different clusters. These clients allow our workloads to request access to the network services, even in different clusters, as is the case for the object detector. As we can see, the connection between the two pods is established in a matter of seconds, and the pod in cluster 1 is receiving data from cluster 2. Another inter-cluster communication mechanism is DLT federation, triggered by the consumer domain for a multi-provider scenario. In this scenario, the provider and consumer domains agree on the federation terms with a blockchain smart contract, which represents a dynamic SLA. And the object detector component is migrated to the provider domain's Kubernetes cluster. We will proceed with an indicative example. We simulate a saturation of the CPU that will trigger the federation. The consumer sends a transaction in the smart contract to announce the desired service deployment with specific requirements. The provider responds by generating a bid offer transaction with the service price. Then, the consumer chooses the offer from the provider domain, and the provider proceeds to deploy the requested federated service. This deployment includes making the federated service accessible by using a load balancer in Kubernetes. Once the deployment is successfully completed, the provider informs the consumer and shares relevant service information, including connection details. Finally, the consumer terminates its object detector component and reroutes the incoming video stream to the newly deployed federated object detector. The results showed that it takes 15 seconds to complete the whole federation process. The second workflow of the application comprises 3 essential components: the encoder, responsible for encoding frames before forwarding the stream; the media server, handling the received stream for distribution and management; and the front end, serving as the user interface for accessing and interacting with the streaming system. Using this workflow, we will proceed with demonstrating the infrastructure layer emulator. First, a description of what is seen on the screen. On the left, the network service frontend with the video streaming, and on the right, the ILE user interface, where the service is represented by the blue line, the MNO scope with the gray background, and the extreme edge nodes are distributed on the black background. There is also a timer to indicate the emulation time. Then, one of the extreme edge nodes will turn off. However, the service will be still running, as 3 more replicas are deployed in the remaining extreme edge nodes. After a while, the orchestrator will deploy the missing replica again in a powered-on extreme edge node. The service is working with only 2 replicas deployed, while the orchestrator chooses another 2 nodes to deploy the missing replicas. Finally, for demonstration purposes, if no replicas are deployed on the extreme edge, the service stops working. This concludes the demonstration.